Welcome. So in this video, I want to do a couple of problems looking at solving for the pH of a buffer solution under a couple different scenarios. So the first problem here is just simply to calculate the pH of a buffer solution. And in this buffer solution, we have 0.05 molar acid and 0.15 molar of our conjugate base. Right? And so the key species here, right, are the acid, and this will be its conjugate base, right? Now, if we have a buffer solution based on an acid, right, it's the same approach we would do to solve for the pH of a weak acid. We're going to set up our ice table and solve in much the same way. So first step here is to set up our equilibrium expression. So we write out the chemical reaction. So we have our acid plus water in equilibrium with our conjugate base plus hydronium. So our initial concentrations here. So our acid is 0.050. Our conjugate base, now this is where we have the big difference, right? In a typical weak acid equilibrium that we've done in the past, right, these have been 0 at the initial. So the difference with a buffer is that we do have an initial concentration of our conjugate base. Our hydronium ion is still approximately 0. So our changes will still be in terms of X. So we're still going to shift toward products because we're going to make some hydronium ion. So we're going to go minus X plus X plus X. So our equilibrium concentrations are going to be 0.050 minus X, 0.150 plus X, and X. So as part of the problem, we were given the Ka of our acid. So we're going to set that up. So 6.5 times 10 to the minus fifth equals, again, our conjugate base times hydronium over the acid. So 0.150 plus X times X over 0.050 minus X. Now, just like all of these acid-base problems that we've been doing, we're usually going to be pretty safe here. And again, making that extra small approximation. You can see even here that we have multiple orders of magnitude between our Ka value and our initial concentration. So we're going to go ahead and do that. Now, that approximation applies to any equilibrium concentration where we've changed by X. So we've added or subtracted an X. So in this case, we're making the assumption that as we move toward equilibrium, neither the acid or the conjugate base change, the X, is going to be significant compared to the original concentration. In other words, it's not going to change by more than 5%. So we're going to make that approximation, whoops, and that's going to allow me to get rid of this X and this X. So I end up with 6.5 times 10 to the minus fifth equals 0.150 times X over 0.050. So we're going to solve through the math. So you can bring this over here, then divide by 0.15, and we get X is equal to 2.2 times 10 to the minus fifth. Okay, so we have our X value. Now, of course, X is equal to hydronium. which is, of course, what we're interested in. So the hydronium ion concentration here is equal to 2.2 times 10 to the minus fifth. And that means the pH is going to be the negative log of 2.2 times 10 to the minus fifth. And so the pH equals 4.66. And that's all there is to it, right? So a couple things to point out, right, is this, for a weak acid pH, right, this might be a little higher than what we'd expect, right? And that's, what we would expect when we have a buffered solution, right? It's not going to be as acidic as just the acid would be because of the presence of a significant amount of the conjugate base already. Now, we did this, but I want to shift to the next slide here and I want to show you a contrast. So, actually maybe I'll try to do it on here so we can put it on the same page. See if I can make room here. And I want to do the same problem, but instead of going through the equilibrium, I'm going to do the Henderson-Hasselbalch equation. So we can kind of show that we can use either approach as long as, when we have this buffering, so when we have buffer systems, as long as the X approximation is valid. So remember, it's pH equals the pKa plus the log of the base concentration. So that's going to be the C7H5O2 minus over the acid concentration. Now, we need to know the pKa. So we have the Ka. So remember, the pKa is simply the negative log of the Ka, which is 6.5 times 10 to the minus 5. And so the pKa equals 4.187. So we have the pH is equal to 4.187 plus the log, and if we look at our problem, our acid concentration is 0.05, our conjugate base is 0.15, so we have the log of 0.15 over 0.05. And so if we solve through this, we get the pH is equal to 4.187 plus 0.477, or the pH equals 4.66. So the idea is we can get the same pH. This is a bit more straightforward than going through the whole ice table thing. Again, the big thing is the X's small approximation has to be valid. And in this case, it clearly is, right? 2.5 times 10 to the negative fifth represents much less than 5% of 0.05. All right, so that's one type of problem. So a second problem that I want to look at is to calculate the pH of a buffer after adding 0.01 moles in this case NaOH, right? So and for the sake of this problem, we're going to assume the volume of solution is 1.0 liters. So we have to break this problem down into two parts, right? The first part, again, is a stoichiometry problem. So we have to figure out how much hydroxide we added and how that affects the amount of our acid and conjugate base that we have. So we're going to do this idea of, we have our reaction of hydroxide plus our acid. So we're adding a base, so it's going to interact with the acidic part of our buffer. So that would be the weak acid to generate water and the conjugate base. Now, before, right, the addition, we had no hydroxide. We had an initial concentration of our acid of 0.05 and an initial concentration of our conjugate base of 0.15. Now, we added hydroxide in the amount of 0.01 moles. So since we added hydroxide, that means our acid is going to go down by 0.01 and our base is going to go up by 0.01. And so afterwards, we've reacted all of hydroxide. This is back down to 0. We've lost 0.01 of our acid, and we've gained 0.01 of our base. So now we have our new moles of acid and base. Now, one of the reasons that makes it nice here is because we're assuming 1 liter, that the moles and the molarity is going to be the same, because we can convert to molarity by dividing by the volume, 1 liter. And so that's why a lot of these problems will just assume a 1 liter volume. If they give you a different volume, well, then of course you would have to calculate, the concentration. But since we were given just the concentrations to start with, and if we're not specified, we can just say we have 1 liter, and that way, the moles and the molarity are interchangeable. Makes it a little bit easier in the math. So now we're going to do the second step. Right? Remember, the second step is the equilibrium problem. Now, we could solve this in an ice table, or we can solve this in the Henderson-Hasselbalch. So I'm going to do the Henderson-Hasselbalch because this is might as well use the easier version, right? There's no reason to do a different version. And so remember, that's going to involve us the equation pH equals pKa plus the log of the base is C7H5O2 minus over the acid. Now, remember from our previous work that the pKa of this acid equaled 4.187. So, and the pH equals 4.187 plus the log of our conjugate base, which is 0.16 now, and the acid, which is 0.04 now after the addition. So if we go ahead and solve this problem, you get a pH 4.79. So not surprisingly, right? Remember the pH of the buffer, right, that we just did before any addition was 4.66. So the pH has risen from 4.66 to 4.79, right? So we're adding some base, not surprising, we're going to get a little bit more basic, right? Because we're losing some of the acid part of our buffer and we're gaining some of the conjugate base. The equilibrium will adjust as we're talking about, and we'll settle out. So this may, so we got about a 0.13 change in pH. No, not insignificant, but much smaller than it would have been. And let's see if I can maybe give you a little bit of contrast here. If we were to say, if we just add the same amount of base to water. So if we just were to add this to not a buffered solution, but just add that NaOH to water, right? 1 liter. What would be the effect on the pH? Well, in this case, the concentration, right? So the molarity of the NaOH is 0.01 divided by 1 liter equals 0.01 molar. So we have hydroxide ion concentration of 0.01 molar. So if I can calculate the pOH equals the negative log of 0.01 equals 2. So we have a pOH of 2. So remember, the pH plus the pOH equals 14. So that means pH plus 2 equals 14, or the pH equals 12. So to get some comparison, if we were to add the same amount of base, same amount of sodium hydroxide to water, the pH would go from presumably 7-ish, right, neutral water, up to 12, right? So a huge change in pH. Whereas if we add that same amount of NaOH to a buffered solution, then we get, a very small change in pH. So this is the idea that we can have with a buffer. So a buffer, again, can allow us to maintain the pH of a solution within a range, even with the addition of strong acid or base. Okay, so that's a couple of problems of working with buffers.